You heard the lady? Do, do, do. Well, I think, Greg, if you have if you want to like sort of give the background to what we're doing or what you were doing, that'd be awesome. Like we can kick it off.
Sure. So, as with all good things in Clojure, this needs to start with a definition. So, uh, I'll start with a definition before the definition, which is what do we mean when we say observability? And I guess I should even preface that by saying this talk is about a library that we've been using internally that I developed and recently open sourced because it seems like there's not a ton of options for this in the Clojure ecosystem right now. And like I've really enjoyed using it, and it's been extremely helpful for us. So it seems like a good idea to release it. And the library is called Ken, and it is a observability instrumentation tool. So I can share my screen here. So it's available on GitHub at Amperity Ken. It's published on Clojures under com.amperity/Ken, since we are now subjected to domain name restrictions on what the group names can be. So a little different than our current libraries, but it is open source. It will hopefully get a 1.0 release as soon as we have finished migrating our internal usage to the open source version. And why did we pick the name Ken? Well, again, starts the definition. So I was looking for a name that was short and succinct because this is instrumentation code, so it's going to show up all sorts of places in our code base. And this was really appealing because it wasn't taken by anything, and it has a couple of nice definitions that relate to observability. And the goal of the library is really to give us a way to instrument our code without coupling us strongly to any particular source of information or destination for that information. There's a bunch of different kinds of places you might want to pull data from, and there's a bunch of different kinds of tools you might want to send that data to. And the idea was like, what if we wrote something that sort of captured the general idea and then let consumers plug in where they wanted? This is also inspired by something that got added to Clojure in 110, which is the tap, which is this kind of global queue you can send stuff to in order to do something with it somewhere else in a decoupled way. And that way you also don't have to like worry about threading something stateful all throughout your code because you want this to be as low friction as possible to use. So I'll actually switch to Clojure doc here, which is great. And we can look through the README. The other thing I want to preface this with, for those of you who maybe aren't as like steeped in the observability terminology and ethos, is observability is distinct from just monitoring or just logging, which are both these like really time-honored concepts and ways to understand how your systems are behaving in deployed context, where logging kind of gives you some information, but it's hard to couple that to other things that are happening because each log line kind of stands on its own. And especially if you have a kind of big stream of logs from all of your systems at once, it can be really challenging to figure out what's happening because you have to match up kind of the lines that are related to each other across multiple services, across like time even. And on the other side, monitoring is the idea of like, okay, I've measured a single thing about my system, like how long did it take to serve this request? And so you go report that to your metrics system, and that puts it in the time series database, and then you can start asking questions like, what is the 99th percentile of my request processing time? What is the 50th percentile? That is really good for understanding the behavior of your system in aggregate, but it becomes challenging when you want to ask questions about a specific sequence of things, like this user got a 500. Okay, well, why? Like, how can we figure out what actions led to that? What was the system doing when that 500 error got thrown? Similarly, monitoring is great when you know upfront what kind of aggregations you want. Like I know I'm interested in the P99 of my request duration. But if I later decide, oh, actually, but I want to be able to break that down like by tenant in the system or by the user in the system, like maybe one user is experiencing 1,000 times the latency of all the other users. Like, well, you're not really going to be able to get that from monitoring system that has pre-aggregated all those numbers for you, because you can't go back after the fact and ask, uh, you know, to break down by this new dimension you've decided to be useful. So observability is kind of pitched as the superset or a higher level concept of you want to just measure stuff about your system. You want to make these like very wide events. You put lots of context into them. And then if you have the right tool, and I'll talk about the one we use later, those can be very powerful because you can go back and ask like questions about this rich data set you've generated by instrumenting your system. In some ways, like, these can feed into those other kinds of systems. And in fact, one of the destinations that we use with Ken is in fact a logging system. Another destination is our monitoring system. So that's what I was getting at when I said this is a way of providing a superset of the data and then later deciding how you want to use that by picking how you feed it into each tool. Also, I can't like see people, so if you have questions, like just feel free to speak out or like say something in chat. Okay, so let's like dive into the actual concepts here. Some of them I've touched on. The most basic thing that you work with is an event, and Ken comes with a defined shape for events that has a couple of like really standard fields you might expect from basically any observability system. So like, what is the thing that happened is the label. When did it happen is the time. How long did it take? And this is in milliseconds. And additionally, some like longer human readable message. And it also captures things like what namespace did you send this from? So you can relate it back to the code that was actually running at the time. There's a few more fields, but we'll get to that in a bit. So in this case, if an event has both a time and a duration, you can think of it as a span of time where this has a start time here, and then it took this many milliseconds, so it has a implied end time as well. In addition to the fields that are built into Ken, the real power comes from being able to associate contextual data with the events that you're sending. So Ken has this, like I said, attempts to be decoupled from where you're getting the data. So it has this notion of a context collector, which are just really functions that run anytime you observe something that try and pull information out of the environment. Some of that information you may know at like process start time and it never changes, like your build version. Some of it might be dynamic, like what is the currently authenticated user, and I want to attach that to every event. So in the example I gave before, if you have this user information associated with all of the events that are relevant for that, then later it becomes possible to ask those questions like, okay, break this down by user, or you know what, I know the email of the user that reported this bug. What if I go back in history and I filter the data I'm looking at to just that user? That makes it a lot easier to find those sorts of needles in haystacks that are so challenging with other kinds of systems like logging and monitoring. And so the way you register these things is just in the Ken context namespace. There's this register. Register static is basically just a helper that wraps a constantly around the value you give it. And the key you provide identifies that collector so that later you can remove it or update it if you want. The flip side of that is what do you do with the events? And so, like I was saying, this is similar to the tap that's built into Clojure. It uses its own so as not to pollute the built-in tap. But all events that you observe get sent to this tap, and then you register subscribing functions that do something with the event. And what they do is totally up to the function you provide. The most basic one, which I'll use later, is this pretty printing. So I just want to see all the events and have them spit out in the REPL so I can see what's going on. In practice, this would probably be something like write this event to a log, or send this event to Honeycomb, or report this, assuming it has the right fields, report this to my monitoring system. And you can have as many of these as you want. They're totally decoupled from each other, and they can take whatever actions are useful for the tooling you want. And similarly, you identify these with a keyword so you can have a handle for them later. And then finally, the way this kind of gets woven together into a full story that you can see in a tracing tool is by keeping track of both an identifier for the total unit of work, the total set of work that is done for a specific action, as well as identifiers for the individual pieces of work that make that up. So say a user clicks a button in your UI, that might cause a request from your UI to your API. That API system might have to make more requests to some other services. Those services in turn might have to talk to a database or a cache. Each of those pieces of work is its own observable event and turns into a span. And by keeping track of the identifier for that whole operation, as well as being able to link those spans to each other by knowing which ones are the parents of which other pieces of work, you can build this like tree of events that gives you a really detailed view of a specific interaction that happened and how all those bits of work are related to each other, which is really like kind of where the magic happens. Once you have this call graph, it becomes possible to like really understand your systems at a deep level. And this is a trivial problem to solve when you have a single process and a single memory space. It's a very hard problem to solve when you start talking about a service-oriented architecture or distributed pattern, which is why this is sometimes also called distributed tracing. And so you can see some additional keys in the events here are the trace ID and span ID, and then this parent ID matches the span ID here. So basically saying that this second event, B, is a child of A. So somehow A caused the event B to happen. Okay, bit of a whirlwind tour. Any questions so far?
I mean, this all seems so, I don't say obvious, but like it all hangs together pretty well. Like, what's kind of the alternative, or what's the thing that you were replacing, I guess, other than like, adding another layer of indirection?
Sure. There are, so I mean, we had logs before this. We had metrics before this. We did not have a good tracing story. So there wasn't a way to kind of tie all this together. So an example, this is rolling out to some of our API services now still. And like we would get 500 warnings, like our monitoring system saw that some of the requests had a 500 status. And you would go to the logs and you would search for 500 and you would find the one line from the API that said, yes, this request had a 500, but the investigation from there could be anywhere from trivial to impossible, depending on how good you were and how obvious it was which other lines in the log were related to this API request. So the ability to tie all this together is, I think, really where the secret sauce is. There are other tracing libraries, I think, for Clojure, but none of them were generalized. There's one that I came across called mulog, which I only found out about after like I'd finished writing Ken, so we didn't adopt it for obvious reasons. But the other thing that Ken solves is the async case. So again, this is sort of much easier when you're working in purely blocking code. But since our services are built on top of an asynchronous computation framework, Manifold, that becomes much trickier to correctly measure how long something took and make sure you're emitting events and propagating the context the correct way across those different thread boundaries. And I'm glad that you said it was obvious, because like the concept part of the README is hopefully very obvious. That means it's a clear problem and hopefully well put together.
But I feel like it wasn't that many years ago that we were talking about, hey, we should really do structured logging, and now it's like that's price of admission, right? That's one instance of application of this kind of framework.
Exactly, yeah. And that switch to structured logging did help a lot. But then you're sort of in a similar boat where you want your events to have a bunch of rich data to put in that structured logging output. Like structured logging doesn't help you if it's like a map with a single key, which is message. So you need some way to get more context into those, and you actually have a very similar problem that Ken tries to solve with these context functions, which is if you have to write every log/info call with all of the keys that you also want to put in that log message. Like, I mean, one, developers are lazy; they're not going to do that. But two, you would probably like the one time you needed the user ID would be the time that you forgot to add it to that log message. So really automating this and making sure that the context is applied everywhere and propagated was another, I think, thing that helped Ken a lot. Cool. So let's talk about the actual way you use this library, which should be pretty quick, and then I can show a little live demo, which will hopefully work. So the most basic thing you can do, so you pull in the namespace ken.core. It's the main API for the library. It's a pretty small surface area. I mean, you do the context registration and the subscription of your functions, on process startup or wherever. And then from then on, it's all about instrumentation. So the most basic thing you can do is just observe an event, and you give it a map, and it sends it to the Ken tap, and you're done. This also collects all the context at that call site, so it knows the namespace, the line you called it on, picks up any dynamic context collection you've set up. So it enriches the event with as much data as possible and then sends it off. Actually, the simplest thing you could do is just observe a keyword or a string, and that is a shorthand for sending an event with just a label. But again, that's not super useful. So the more data you can put into these events, the better. In practice, actually, we found that the observe call is not used very often. By far the bread and butter of this library is Ken watch. And so this is a macro that wraps around a body of expressions, keeps track of how long that body took to evaluate, and then emits an observed event at the end of that. So here, this is the shorthand for an event with this label. It's still going to collect all the context at the call site, and then it's going to evaluate these expressions, send the event with the additional timing information, and then it returns the value of whatever the last expression was. So just like a do or a let or anything you're familiar with in Clojure. Importantly, this also is compatible with Manifold, which is the async framework I talked about. And for those of you who haven't seen it, this is basically saying run crunch numbers with this argument, but do it on a new thread and give me back a promise, effectively, a deferred value that will only be realized once that calculation is complete. So this expression actually returns immediately, giving you that deferred value. And chain is a way of saying, call this function on the result of this deferred value only once it's ready, and handle stuff like if an exception gets thrown, it short circuits the chain and all that sort of stuff. And again, this outer expression returns a new deferred value. So if Ken watch were not async aware, it would be telling you, hey, this operation took 0.001 milliseconds, which is not helpful. So this can tell whether it's been given back a deferred value or not, and will correctly send the timed event, as well as making sure that the tracing information gets propagated to the different threads that may be inside this. You can also provide additional values in that first argument to watch. So this is another way to provide that richer data when you know it up front. And that will be part of the event that gets emitted at the end. And the other thing, which I guess I didn't include in the README here, oh yeah. So if there was another Ken watch inside this one, this also handles the tracing information. So this Ken watch will have some trace ID assigned, as well as its own span. And any watches you do inside this, even if they're in other functions or on other threads, will pick up that parent span and trace ID and correctly tag themselves so that later you can reassemble these events into a full trace. Sometimes you don't know information up front, maybe because you had to calculate it later, or maybe it's the result of some of the work you're doing, or maybe something went wrong and you find that out later. So Ken has this concept called annotations, which let you add information to the enclosing span procedurally. So like here, we're checking if X is a foo, and if so, we're adding this foo true attribute to the outermost span here that we're watching. Ken time is kind of like Ken watch in that it measures how long the expressions inside it took to run. But instead of its own span, it just annotates the enclosing span with that value in milliseconds. So a good example of this is like in our APIs, we have a span which corresponds to how long it took to serve that request in total. And we also have information about like how long did it take to encode the response body and how long did it take to decode the request body. Those are typically like less than a millisecond or a couple milliseconds each. That's not really interesting enough to be its own whole event, but it is good to know how long that took. So time is a kind of middle ground, which lets you record that information in a more lightweight fashion. And then finally, error here is another kind of annotation that sets a couple fields. So it sets the event level to error. It sets the exception as one of the fields on the event. And it also sets the fault flag on the event, which means like, hey, something bad happened here. And then the last main thing here that's useful to know is this with context call. So I talked about registering context collectors, which are these kind of global functions that get run to pick up attributes about the surrounding environment when the call is made. Sometimes you don't want something global though. Sometimes you know some data that are useful to have on all of the events within a certain context, but you don't necessarily want to set on everything. So this could be an example where you could do this if you knew that foo and bar are relevant pieces of information for all the work I'm about to do here, even if there's like several layers of nesting. So I'm going to set this with context call, and this is basically a local context that will propagate to all of the spans underneath it without stuff happening like elsewhere in your code having to pick these up. So this can be useful if you want a easy way of using context without having to like manage your own dynamic variables and stuff like that. And finally, Ken supports sampling. This is mostly useful when you have a large number of events that are very similar. So like we have a service which like manages our tenant information. And so like basically every service call we make that has a side effect checks to see if that tenant is in the right state or not. So that's a good candidate for sampling where it's not always interesting information, but it's also mostly useful when you get to a higher volume of events. So it won't apply to everyone. But it gives you a programmatic way to probabilistically keep a subset of your events in a way that makes sure you preserve the integrity of traces so that if you decide you're going to drop the trace early on, you don't want to then record a bunch of spans later down the call chain because they won't have a root trace to assemble into. Cool. And so there's one other companion library to this, which is Ken Honeycomb. So we use Honeycomb as our one of our observability tools, and this has the integration with that, which we use Stuart Sierra's component library to manage our services. So this is a component that on start registers the Ken subscription, which wires your events to Honeycomb, and on stop unsubscribes that. So really simple. I won't get too big into this. So you'll be able to see the effects of it, hopefully, when I get to Honeycomb. Okay, let's try some demoing. So I'm just in the Ken project here, and I'm in just a regular Leiningen REPL. So let's see, the most, oops. So I already did this to subscribe Pretty Printer to the tap. So this will print out all of the events that get sent. Here's an example of using that with context, and I'm just going to observe something. So observe returns true because the event was accepted by the tap. And you can see that it has collected some information for me in addition to the label, which is the only thing I really provided. to the observe call. And it's also picked up the context I sent. So you can see the user ID and username here at the bottom. This got tracing information, although there was no other parent to this. So this is the root level trace and just generated a new one. Recorded the time, but there's no duration associated with this because observe is a kind of like point in time way of sending events. I can also do like a can watch. And so that returns the foo, which is the last value in the expression. And then I get the event, which this time does include a duration. This also has adopted, I didn't talk about this too much, but adopts the idea of log levels. They don't directly impact anything, but certainly when you're talking about sending these to a like logging system, it can be very useful to map those. And you can do stuff like default to info or debug, and then when you catch an exception, you can annotate that level to be a warning or an error. Let's see, what else is cool to do? Another example I did before this. Okay, yeah, okay, this one is kind of complicated. So this is using that same with context. It's doing a watch. This is mimicking a like API call. So let's say that this is outer watches our request handler. We're doing some asynchronous calculation here. Let's say we need to authenticate the user first, and that takes about a second. Returns us some auth data. And then we're going to look up the user's profile from the database because that's where it's stored. And in addition to the label here, I know the SQL statement that I'm going to use. And this turns out to be super handy to have in your observability tools. That only takes about 100 milliseconds. And then that returns me a bunch of information about the user. So that returns a deferred value here. This is one of those promises that I was talking about. And initially it's pending because it hasn't been fulfilled. But then you can see the events get sent. So the first event we see is the authenticate user call because that's happening inside the outermost call. We see the label, the thread it's on. So this happened, you can see not on the nREPL thread. The trace ID for ASF, and it has that additional user information I got from the outer context. The second event we see is, as you might expect, the SQL call. So much shorter duration there, and I get the attached SQL statement. You can see the thread or the trace ID matches the outer one here, and the parent ID matches the outermost authenticate call. And then finally we get the enclosing span. This one has the same trace ID, and we should see that this started before any of the other ones. Yeah, by about a second or 100th of a millisecond in the case of this first call, because it got kicked off right away. Oh, and if I deref that, I get the end result of that deferred call, which is the user's profile. So this is it starts getting a little tricky to piece together in the REPL, which is another good example of why even if you're just doing structured logging and dumping all this information out, it can still be kind of hard to piece together what happened. And so this is where a tool like Honeycomb or Lightstep or Zipkin even really shines. So let's look at some stuff. Okay, that should do it. Group by URI, order by count. Okay, so what I'm looking at, what I asked Honeycomb to show me is show me the count and the heat map where the span has a request URI. So this should correspond to our API spans, grouped by URI and then ordered by count. And so you can see some interesting stuff here. We've got a bunch of calls, pretty steady state to this SSE endpoint. Down here, we've got config compare. There's a big spike here. That's interesting. Okay, it looks like a lot of them are this unique Amperity ID count. But the heat map is also, I think, super useful, and that's something that Honeycomb is really good at. So it shows you basically blocks in a grid where the x-axis is time and the y-axis in this case is duration in milliseconds. So I can see that there's a bunch of them down here that are pretty fast, and a lot of them happen that way. There's two interesting areas though. There's this spike here, which we sort of already figured out up on the count. There's also this like pattern up here, which I'm not really sure of. Honeycomb has this feature called bubble up, which is really useful, where you can click and drag around a bunch of data. So like, let's find out what this pattern is all about. And then it breaks down in a really flexible way all of the information you provide, and tries to show you what's different. So like right away you can see, okay, 100% of the things I selected were puts, whereas only 0.1% in the total data set. So like everything I'm looking at here are puts. So that's pretty interesting. And then this basically is the whole story, which is that, hey, all of the things you selected were this one endpoint. So if I were interested in like why this was slow, that would be a good thing to go look at. I could figure out, okay, I know specifically what code path is getting called here. And then this is just the message, so that's not as interesting. The request size, okay. And resource ID, similarly, this tells us where to go look at the thing. So bubble up's really cool, and I could probably do the same thing here to figure out what this is about. So here's really interesting too. I was talking about being able to tell what's going on by user. So I know this spike of activity was actually caused by one of our engineers who was working with, this is dev, so it's almost definitely going to be one of our engineers. But if this were an external user, I could know like who was causing the activity and who was potentially impacted by it. What is this? Client IP, tenant ID, Kendo event label. Okay. But the real magic is once you start working with traces. So let's look at one of these events. They took about 6 seconds, and there's 79 spans in this trace. So that's like all of the different pieces of work that had to happen to serve this. So if I open that trace, I can get a view of like what actually went down in order to satisfy this request. And on the right side, so this is the trace of like everything that happened, and on the right side is all the information we sent. So this is where it can be really useful to just add additional context that you know about the events that are happening. So like, what if there was a bug in one of our content type codecs? Well, the fact that I have this content type as one of the event attributes means that in that bubble up view, we would have been able to see statistically important differences in the content types that are getting passed around. Or if the user gets an error that includes the like request ID generated by our HTTP server, I can now do a search and like actually look up the associated data about that request in this tool. So we've got a bunch of stuff about the method, the request size, the URI, how long it took to encode, how big things were, the IP addresses, the authenticated user, all of this stuff. And then as I trace that down, I can see like, let's first look at the like high level things. So first we called authenticate token because the first thing we had to do was check that the user's authentication was valid. Then we looked at the tenant that they were operating on. Then for some reason we looked at the tenant again, and so this would be interesting to dig into why that was. And then most of the work was in this compare versions call. And then the other interesting thing you can now kind of get from this is seeing, there's actually quite a gap between the end of this span and when we consider the request complete. So it'd be interesting to look into the code and figure out, is this gap because we're missing instrumentation on something that happened, or did it spend a long time serializing the response, or what happened here? The other thing that is cool, I bet, if we look at this, so this get tenant call was for what tenant? Acme2 Max Bass, or Max Base is the name of the ID of the tenant. And in this case, since we make this call so often, there's a cache associated with it. And that client actually annotates the span with the cache result. So here we can see this was a cache miss. So it went and actually talked to the tenant service, which then had to talk to the database. It actually ran, we can see the SQL that got run in order to load this data. The second time here, this was also a cache miss, interesting. So it did have to talk to the tenant service again. So these may have been made in parallel, actually. And then as we dig deeper, we can really get down into all of the work that had to happen to satisfy this request. And in fact, we can see the same get tenant call was made by this service to tenant service. So it actually wound up returning the information about this same tenant quite a bit. And then this is kind of a classic example of a waterfall of request pages happening in a database. So if we wanted to optimize this call, which is taking a decent amount of time here, a pretty clear thing to do would be to increase the page size, so we didn't have to spend so many cycles going back and forth, round tripping the database. And then one more example I want to give. This is a demo I gave at our engineering meeting last week, where I had done some additional work to get the integration working all the way from the UI. So you can see the system here is our web UI. And this is actually measuring me clicking a button in the UI to run a query in our system. And then this tracks from the user's browser all the way through our API into our backend systems to first kick off the query. And then there's a couple of 1 second polling intervals where it's asking hey, is this thing done yet? Is this thing done yet? And I can, again, get all the way down into the interaction with the database, what feature flags are enabled, how the overrides are set up. And then once the polling says that, hey, yes, this query is correct, then I can go and dig into how it got the results back to the user, as it has to talk to 3 different services. So it's super powerful to be able to have this insight into your system, both on a single operation interaction level and on the high level, what's going on in aggregate and how can I break down weird stuff that I see, because humans are very good at visual pattern recognition, much more so than staring at a wall of data attributes like this and trying to piece together what happened. So yeah, that's pretty much the end of the prepared content. Happy to answer questions or demo other stuff if people want to know more.
Yeah, I'm definitely very curious. We use New Relic very heavily, and so they do kind of have the distributed tracing, but of course you only get to trace things that New Relic thinks are important or that you've annotated, so it's kind of a pain. You mentioned integration with Manifold, and I looked in the repo and I see Manifold is a direct dependency of this. What happens if you use sort of regular futures or other async stuff?
I think it would still work. Manifold is compatible with Clojure's built-in features. It's less efficient since there's not a direct way to register callbacks, but it also works with things like promises and delays and stuff. So I think that would still work. The other part is the dynamic variable propagation, and I'm pretty sure Clojure's normal futures do that
Yeah.
correctly as well.
Okay.
So that's the mechanism that Ken uses to propagate all the stuff around, like what the current span is, what the trace identifiers are, and all that.
And what special stuff do you have to do to tie up a UI to a server-side thing? Is it just the trace ID that has to be passed across on the requests?
That's the main thing. So the core definitions in I guess this doesn't show specs, but the core stuff in the Ken library is CLJC, so it's cross-compilable. So you can use the same like data shape, and then the main thing you have to do is collect those events and then have a way of getting them back to your tracing tool of choice. So in our case, we have a like endpoint that the UI can post a batch of events to after it's collected them. But you're correct that the main thing you need to tie together across the UI and API divide, or really any client, I guess, doesn't have to be a browser, is that trace ID and the span ID, so that the API side knows, what trace ID should I use and what parent should I use when I have the span on my end.
Okay. Okay.
And the trace namespace here has a couple of functions for using a standard header for that.
That's very cool. Very cool indeed.
Yeah, we're still working through the integration there on our end, but it's been pretty good so far.
Hey, Greg. One of the questions that I had was, to my knowledge, one of the most notable prior arts here was Saeed. I haven't used Saeed personally, but do you know how it compares?
How do you spell that?
Sayd. Author did a talk at Strange Loop several years ago, I believe.
This one?
Yes.
I'm not familiar with this.
Okay. It's been a while since I saw the talk, but as I remember, it had sort of an emphasis on observing variables over time as opposed to tracing variables as they hopped through the code. You'd sort of get a layout of the this variable took this state at this time, and instead of sort of the built-in debugger in Cider where it has that graphical hopping from one point in the code to the other. Yeah.
Okay, I think I have seen this a long time ago, actually. I would characterize the main difference as this is a more of a debugger for the like function level scope. You would probably not want this much detail in a tracing system that was like operating at the level of your services and APIs.
Oh, for sure.
So yeah, I see them as like occupying similar spaces, but
there's a Venn
scales.
diagram here.
Yeah, so like this is more useful in local development for like understanding how your code works at the like namespace level, whereas Ken is targeting like how your system as a whole works by tracing through all of the different operations that are happening. Because like it's definitely not the case that like every function we write is instrumented with Ken. There's typically chunks of work that make sense to measure as a span that are like have a meaningful amount of information with them.
Now, when I looked at the GitHub page for Ken and it used the term instrument, that sort of made me assume that you do use it to some extent as a debugger, that you use it during the development of a function. Am I wrong there? Is it really aimed primarily at documenting code that's live?
It does provide useful information locally, although actually largely with the log output, since we don't send
Right.
stuff to Honeycomb like from a REPL by default.
Mhm.
But the structured logging is still useful. I mean, it's a little intentionally less verbose than the like raw pretty printing I'm doing here. But it's still useful to be able to see. I might have some examples here. So like this is an example of me doing some development on an API locally. And so it's a little more condensed, but this is really the same information as is getting reported by the instrumentation. So it still gives information about what's going on in the code. Not as visually easy to parse as the other one, but it's, again, also not going to be at the level of like every single function that gets called. So it's
Right,
more
so-
about choosing when to apply it.
Right. So for you personally, for example, you don't, this isn't the first tool that you would turn to if you wanted to instrument a function for development. Am I correct in that?
Yeah, I mean, I'm
Okay.
in that case much more likely to just throw some like print lines in there or something.
Right.
If it's just
Right.
at my REPL, or eval pieces of it in the REPL and see if the individual pieces are giving me the result I expect.
Yep. Atom, that and atoms are great. Yeah. I'm biased.
Or the Clojure core tap.
Yeah, like I said, definitely the tap was an inspiration for this.
I should mention for the record, guys, if you saw me glance towards the camera, that's because I drive a Mini Cooper, and the mileage, the speedometer is right next to my phone. It's not because I was taking my eyes off the road.
Good, good.
I have one question. What's the best way to use Ken to instrument and observe something where the work is not necessarily happening in like one request chain, but maybe something like there are many different threads that may pick up something and do a little work and then put it back down, kind of like a state machine.
So there's two answers to that. One is you're not limited to using the kind of automatic propagation of Ken's trace IDs, like like watch is nice because it will automatically wire everything together for you, but in that case you could generate your own trace ID to represent that kind of high level unit of work, and then just manually provide it to each of the places when you have a thread picking up a job as part of that. That would work just fine. And in fact, the UI implementation is a lot more like that, because there isn't really a notion of multiple threads and like dynamic bindings. It's just one thread doing things one after another. So you have to do more passing around of the tracing information. The other is that Honeycomb has a feature that we're not really making use of yet, which is, let's see if I can see it here. Definitions maybe? Yeah, which is this idea of a link span ID or link trace ID. And that gives you a way to connect kind of different top level pieces of work to each other where there isn't really necessarily a parent-child relationship between those two things. It's just they are related, but are more like siblings. We haven't really made use of this yet, but that is one way, at least Honeycomb specific, to attach that information. The other thing is, like, unless you really need to see them all in like one trace view like this, just giving them the same like value for one of these attributes, like the same job ID or something, gives you a way to look up that information across multiple traces. So that might be a kind of simpler way to do it too.
Okay, thanks. The link trace ID is something I hadn't heard of before, and that sounds like maybe worth taking a second look at.
I'd love to play around with that. We just haven't had a use case for it yet.
Greg, do you have a way to expand Ken to also include normal login? And I'm asking this because, for instance, I used to work a lot with Datadog, and Datadog had this interesting feature. I think that they were getting ready to implement OpenTelemetry protocol on their side. And whenever you saw any trend going on in their logs, you could right-click on any of these trends and ask Datadog to show you interesting information that happened around that log, either by time or by tagging. And then it would bring traces and it would bring APM information, but it was because they were using kind of like the same backend to tie all that together. Is there any way to expand Ken to, I mean, I would not ask to implement OpenTelemetry, given that that's a completely different animal, but at least to include some logging information.
I mean, there's no reason you couldn't build a OpenTelemetry output for Ken. There is so in our logging library, the way we do Ken integration is, so we use Timber, but on top of SLF4j. So Timber is really just to give us a way to kind of inject some Clojure functionality while using a backend that's still fairly performant. But we use this middleware, which is kind of neat because it is almost like bidirectional with Ken. So when a Ken event happens, this log event function at the top here forwards that to Timber to get logged. So stuff like Ken observe, Ken watch, etc., make their way to logs as an output for structured logging. But we also enrich regular log statements. So if you just called like Clojure tools logging /info or something in our code, because we obviously had a bunch of that already when we started this project, that uses Ken's registered context collectors to pick up the same kind of source of information from the environment that Ken does. So we enrich those log events in the same way that Ken events are, and that includes the trace and the parent ID. So in all of our existing code, once that is inside a outermost span or something, or it's part of the tracing call graph, those log statements also get this message attached. So right now, these log statements like don't go to Honeycomb. I think Honeycomb recently launched a feature that would support logging better. So you'd be able to see those log statements in the Honeycomb UI as well. But including the context information and the trace information here has made it pretty useful. So when you do see stuff in the logs, you can then tie it back to a trace that you can go look up in Honeycomb or other tools. Not sure if that was exactly what you were getting at.
Yeah, that's perfect. I mean, I've seen that Honeycomb has an OpenTelemetry collector that they have implemented, but we're not using that kind of collector yet. But if we were able to structure the data according to the OpenTelemetry protocol, we could actually send them that, and they could take advantage of that and show us all kinds of information, better visualization of that information.
Cool. I think this this span event annotation type is what we would use in Honeycomb for log messages. And I think you would be able to see the log information on the side here if I understood the usage of that correctly. But we haven't, like I said, part of it we haven't gotten to exploring yet. Well, if there aren't further questions, like I said, these two libraries are available for usage now. I have a approximately 3,000 line PR to migrate our internal usage from the internal version of Ken to the open source version. Nothing bothers me more, or there's a guaranteed way to get open source projects to rot, which is a company that just copies the code and then doesn't actually start using it themselves. So once we are migrated and all of our systems are on the open source version, I'll cut 1.0 releases of these and do some broader announcements. So this is a bit of a sneak peek. Hopefully it was interesting to everyone, and go forth and observe your systems.
Thanks, Greg. Yeah, super interesting. Definitely interesting for us. Our new use of New Relic.
Yeah, be cool to see a. I guess I don't know what the API for New Relic is like, but it'd be cool to see a Ken output for that.
Yes, that would be interesting. If we go down that path, I will definitely make an open source version of that. I will go create a WS ticket in our work repo for that to have a look at it.
Cool. Yeah, I mean the Honeycomb integration was, it's leveraging their SDK, but it was really simple to write. It's only, let's see,
What version of New Relic are you using, Sean? Is
You mean
the
the
new one that is
libraries
on
or
the new one that is under the one.newrelic.com?
Yeah, we're under New Relic 1, and we've actually just switched all of our, because we used to use the old New Relic's metrics library, and they VOL'd that, and it goes away completely in less than 2 weeks, I think. And we switched over to the Telemetry library, which is actually kind of much nicer to use, although it was a lot more work to set up. And we were double publishing for a while until we had everything under control, because we had so many alerts based on the old plugin metrics. But we literally found ourselves completely plugin free as of, I think, Monday this week.
Yeah, I had a very bad experience with New Relic. They pretty much migrated our account forcibly, and suddenly we couldn't see things that we were sending them. They were collecting the data, but they were not. I think that the new interface, I think they had some pressure by the industry. All these honeycombs and Datadogs were actually really eating to their share, and their new interface was much prettier, but they didn't have like all the information that we actually were using.
Yeah, it definitely, the migration from the old New Relic to the New Relic 1 was bumpy in places. The only real problem we've ever had with the service, apart from just occasional outages when your monitoring service knows that it's down, which is like, is they have certain inherent limits on unique IDs that they track for you, and they will just very conveniently just shut you off if you have a rogue process that, for example, if you are accidentally logging things under, your trace ID, your UUID, and every single request got a unique ID in the transactions, they would just simply shut you off, and you wouldn't be able to get at the data at all, and you'd have to walk them through and say, okay, delete everything that looks like this, or delete everything that's older than a certain period of time. And we've had that happen probably half a dozen times. And of course, every single time, yes, it's our fault for sending transaction and IDs that are, too unique and should have been aggregated. But you get no indication that this is going to happen to you. everything looks fine, and then suddenly your graphs have no information in them, which that's been frustrating. But like I say, it's good enough for a lot of stuff. We have a JavaScript front end, and they send a lot of data to New Relic. I haven't checked the distributed tracing from the front end to the back end, but certainly across all of the distributed components on the back end, it does work. We just don't have enough stuff traced because it's a giant pain to trace stuff, because a lot of times you have to have Java annotations to trace stuff with New Relic. So its API is pretty horrible unless you're using Java. This looks much nicer. And the idea of being able to peel it out into log files, and some of it going to New Relic and or Honeycomb, that's something else I'm going to put a note to look at. That's very appealing. It's very interesting. Also, just to be able to stream all the data somewhere and even just let it drop on the floor, so you can at least get everything annotated, is nice, because then you could tap into it while you're developing.
I've definitely like subscribing that pretty printer to the Ken tap has been extremely useful when I need to like really dig into some information about what's happening, because the bias is to add more information to your events and like be able to use it later.
Right.
We definitely had that same kind of cardinality problem with our monitoring system, where you had to be. I mean, we run it ourselves, and it's InfluxDB, and it's definitely shown some strain at times when we accidentally put something too high cardinality into the like indexed part of the data, and then tried to like do a group by, or even just it tried to autocomplete some values for that field and kind of fell over. So Honeycomb's been really nice. We just haven't had any cardinality issues, and that's part of their premise, is like send us as much data as you want, as varied as you want, and we will run the queries over it kind of on demand.
Yeah, we're also using Elasticsearch on the Elastic Cloud stuff, and they've pinged us a couple of times to dump logging information into it, which, yeah, that might also be worth looking at as a client for this Ken. So yeah.
Yeah, hopefully the logging library is a little more coupled internally, but I'm hoping to take that and the metrics integration and open source those as well.
Cool.
You said take that and the what integration?
Our metrics integration. So we use Riemann as our kind of monitoring system.
Okay.
And then that stores data in Influx, and then we have Grafana as a kind of dashboard front end on top of that.
Okay.
But there's also an integration piece I wrote for Ken to Riemann.
Okay.
So it watches the tap, and if it doesn't record everything, but if you like flag an event and say like, hey, I want to record this metric as part of it, it'll take that event and also send it to our monitoring system.
Okay, I think I'm missing the distinction between observability and monitoring. So where does Riemann fit in where Honeycomb does not?
So Riemann is where we put most of our alarm logic. So it lets you write, I mean, it's based on Clojure, which is one of the reasons it's so powerful. But it lets you write this kind of metrics stream-oriented logic that lets you do things that are pretty hard to express with a more simplistic, like, I want to set a threshold and get alerted when a value crosses that threshold.
Okay.
So like we have stuff that rolls up like all of the 500s that we've seen in the last hour, and then groups those into a single event and like post it to Slack, and might page an on-call, or like calculate the cache hit and miss ratio across like all the clients of this distributed service. since those are each local caches, and then like publish an aggregate metric that we can look at on the dashboard. So some stuff that's like I said, pretty challenging to express unless you're able to write code for it.
Right.
And Riemann comes out of the box with a bunch of that kind of stream logic. It is explicitly stateless though, in the sense that there's no like state persisted on disk. So that's why we need a separate system like Influx to store the time series data. But the fact that it's stateless makes Riemann like ridiculously fast. Like we're handling, I think, 40,000 metrics events per second on a single virtual machine in AWS. So pretty fast.
Cool. Cool. Thank you.
Well, that seems like a reasonable stopping point. I might go and grab some dinner.
Thanks, Greg.
Yeah, thanks for coming, everyone.
Thank you.